YouTube channel. Today we'll be looking at electronic theories in organic chemistry. Now, the introduction. Well, we'll be looking at atoms. Atoms consist of protons, neutrons, and electrons. Yes, we know that atom is the building block of matter, and it consists of the proton, the neutron, and the electrons. With the proton and neutron located at the nucleus of the atom, while the electrons orbiting round the nucleus. The electron orbits around the nucleus, and we also see that the protons carry positive charges, then neutrons carries neutral charge, no charge, and the electron carries the negative charge. Also, the arrangement of electrons around the nucleus of the atom will determine its chemical properties. It is essential in chemical reactions, in chemical bondings, and the rest. Only the electrons participate in chemical bonding. Now look at the Bohr's theory. The Bohr's theory. Now we know there were several theories proposed by scientists in time past, but this Bohr theory was outstanding. It stood out from the rest of them. It likely produced more clearer view of the atom. So now I want to look at what he proposed, what he said. Now we see that the Bohr's theory proposed that electrons orbit the nucleus in specific circular orbits. Yes, each associated with a definite energy level. He proposed that electrons exist in orbits with definite energy levels. Now we can see the orbits that the electrons the electrons orbit around. The first energy level, the second energy level or shell, and this third energy level or shell. And these shells, they are represented by alphabets called the KLMN notation. They represent the shells. K is the first shell, L is the second shell, M is the third shell, and so on. Also, electrons in a particular orbit do not radiate energy. They do not radiate energy unless they absorb enough energy to jump to a higher energy level known as the excited state. Electrons absorb energy before they can jump to a higher energy level. As you can see in this diagram, they jump to a higher energy level because they have absorbed energy. Also, when they are in that energy level, they emit that same amount of energy, that specific amount of energy, and jump down to the state they were before or to the ground state, releasing energy as light in form of light. They emit that energy in form of light. Also, we saw that the theory was rejected due to its contradiction with the Einstein uncertainty principle, which states that position and velocity of electrons cannot be known simultaneously with great accuracy. For the Bohr's model, it said the the position and the velocity of electrons can be known with great accuracy, which is in contradiction with the Einstein uncertainty theory. Now move to the modern theory. What is the modern theory all about? The modern theory is just telling us that the atoms, the electrons, they orbit around the nucleus in in predictable, like in areas where you can find high probability of electrons, where there is high probability of electrons. not like the Bohr's model that is saying that electrons they are located at specific orbitals, specific energy level. This modern theory is telling us that atoms they occupy a specific region, dense region. They are dense region or they are so lighter region as they move away from the nucleus. As you can see in this diagram, you can see this blue color. This blue color closer to this nucleus at this center here, we are seeing that it is more thicker than this outer color, indicating that electrons they are mostly found around this level, this region close to the nucleus than at this outer region away from the nucleus. Also, we see that each orbital is described by three sets of quantum numbers, indicating its energy level, which is the principal quantum number, its shape, the azimuthal quantum number, and its orientation, its spatial orientation, the magnetic quantum number. So now I want to look at the principal quantum number. The principal quantum number is represented by the symbol n and determines the main energy level and size of the orbital. Yes, the principal quantum number determines the size of the orbital and also the energy level or the shell, energy level or the shell of the orbital, whether it is a K shell, whether it's an L shell, M shell, and so on. So therefore, we can see that the principal quantum number we have values of 1, 2, 3, and so forth. 1 will tell us that it is a K shell. 2 is telling us that it is an L shell. 3 is telling us that it's an M shell. Also, we see that the azimuthal quantum number is telling us that is representing the shape of the orbital, whether it's an S orbital represented by these symbols S, P, D, and F. Before we move on to this, the azimuthal quantum number is represented by the letter L. The azimuthal quantum number is represented by the letter L, and these are the symbols that it represents the shape of the orbitals, with S indicating a spherical shape, P a dumbbell shape, D a double dumbbell shape, and F a complex shape. So it tells us the shape of the orbital. Then we look at the magnetic quantum number M, telling us the spatial orientation of the orbital. The spatial orientation of the orbital. So we can see the diagrams of all the quantum number here. We can see the principal quantum number telling us the distance of the electrons from the nucleus, the size of the shells, the azimuthal quantum number telling us the shape of the orbital, the magnetic quantum number telling us the orientation of the orbital, and also we have another additional quantum number, although not officially a quantum number, but is important in determining the orientation of electrons around the orbital, around the nucleus, which is called the spin quantum number. The spin quantum number. The spin quantum number is telling us how electrons are arranged in an orbital. Because naturally, in an orbital, we can only have a maximum of two electrons. Two electrons, one facing up and one facing down. So this um this tells us this thing is explained by the spin quantum number, with one electron facing up, which is of lower energy, and the electrons facing down, which is of higher energy than this one in a specific orbital. So we see the rules governing the arrangement of electrons, the Alba principle. We can see the Alba principle, we can see the Pauli's exclusion principle, and the Ohm's rule. The Albert principle is telling us that electrons feel lower energy first before feeling of higher energy levels. The Pauli's exclusion principle is telling us that the the no two orbital or no two electron in a specific orbital can have the same values of all the four quantum number. No two electron in a given orbital or no two electron in any orbital can have the same values of all the four quantum number. In a situation whereby they may have the same values of all the quantum number, the spin will not be the same. One must face up and the other face down. So that's what the Pauli's exclusion theory is telling us. And the last one is the Horn's rule. Horn's rule is telling us that electrons go singly in an orbital before pairing occur. In a scenario like in the feeling of the p orbital, we see that p orbitals they have three shares, three orbitals in them, which is represented as ps, py, and pz. So in a scenario whereby, let me say for carbon has six electrons. So therefore we'll first start with the first share, one s orbital with two electrons, 1 2. We are left with 4. So we move to the second shell, and we fill it 1 2. We are left with remaining 2 from the electrons. Now fill it. When we are filling this place, we will not just fill it because we are filling there. This place is telling us because there's only one orbital we have in the s orbital. So there's only one degenerate orbital we have in the s orbital. But in the p orbital, we have 3 degenerate orbital. So we'll fill it singly 1 2. So completing the 6 electrons. How there were another electrons, like if in nitrogen, could have filled here first before we start pairing. But for carbon, this is the electronic configuration of carbon. I may not have written it well, but just take note of this. Now we'll look at the orbital hybridization in carbon. See that hybridization is the formation of new orbitals by combining two or more orbitals with different energy, with different shape and with different size. Like we can combine an s orbital with a p orbital. We can also combine an s orbital with two p orbitals and so on. Now we want to look at what is tetravalency. What is tetravalency? Now, carbon atoms typically bond with other elements using their orbitals and unpaired electrons. They bond with other elements using their orbitals and unpaired electrons, and they typically undergo tetravalency, which is they can form 4 bonds. They can form 4 bonds because they have 4 unpaired electrons in their outermost shell. They can form 4 bonds. And to explain this carbon tetravalency, we need to look at hybridizations, three hybridizations, which are the sp3 hybridization, the sp2 hybridization, and the sp hybridization. Looking at the sp3 hybridization, we see that it involves the mixing of 2s orbital and 3p orbitals of carbon to form new hybrid orbitals. Like for example, the carbon atom, it has 1 share, p share, like this. So for this first 1s, it has two electrons, 1 and 2. Then for this 2s, it has two electrons because carbon has 6 electrons. But it carbon forms its bond in the excited state. So one electron that's supposed to be here will flip, will move to this other side. As you can see, that last time I just put the 2 here and just put 1 here. But since in its excited state, one electron will move from this 2s and jump to this place. Now we have all the orbitals filled. So this sp theory is telling us that there's a missing of one s orbital and all the three p orbitals. All the three p orbitals, the px, the py, and the pz, to form this sp3. And the number of sp3 formed, there are 4, which is 1, 2, 3, 4. 1 will miss to this one, these 3 will miss, so to form 4 sp3 orbitals. It's an hybrid. Also we see that this sp3 orbital formed, this sp3 orbital, this 4, it has lesser energy than the 2p orbital, and it has higher energy than the 2s orbital. So they are in between. They are in between the 2s and the 2p orbital. So they have higher energy than the 2s and lower energy than the 2p orbital. Now move on to the next concept. The sp3 orbitals have different shape from the p and s orbital. Yes, the s orbital has a spherical shape and the p orbital has this dumbbell shape. This dumbbell shape. So when they mix together, they will form something like, but in most diagrams they will just make it simple. Something like this. Make it like this in most diagram. So because this note is somehow negligible, so you just make it like this. And so this is the sp3 orbital. This is the sp3 orbital. This is its shape. It has a different shape than the s orbital and the p orbital. Also, in the excited state, the sp3 orbitals are oriented at 109.5 degree to each other. The sp3 orbital, they are oriented at 109.5 degree to each other. So this is their orientation to each other. Note this, 109.5 degree to each other, as you can see in these diagrams. So this is the angle between each ones. Okay, now we'll be looking at the sp2 orbital hybridization. Now this hybridization is simply the missing of one s orbital and two p orbitals. They mix together to form the sp2 orbital. These orbitals are known as the sp2 orbitals and are of equivalent energy. They are of equivalent energy and are displayed along the apex of a triangle with an angle of 120 between them. So they are typically represented like this, something like this. This is a carbon atom. So we can see somehow like a triangle structure here. So this is the sp2 orbital, the missing of one s orbital and two p orbital. Also, we can see that this sp2 orbital, how are they formed? First, we know carbon has fair share although this shell is the inner shell, so it's not really participating in the chemical bonding process, this one s2. So what we are interested in is in this second shell, which is the 2s and the 2p orbitals. So this one has only one electron because its carbon form is tetravalent bond in the excited state, so it will just fill these three orbitals of the 2p. So one electron from here flip to this other side to occupy this last orbital. Now the sp2, how is it formed? So the sp2 is formed from the sp2. We can see that one s will mix with two orbital, therefore we have sp2 and one unhybridized p orbital, one unhybridized p orbital, the sp2 and the p orbital, the unhybridized or pure orbital. This p orbital did not participate in the hybridization. So you see that one 2p orbital remain unhybridized and is perpendicular to the plane of the sp2. It is at 90 degrees to the sp2 orbital. Also, the sp2 orbital is used in the formation of bonds in alkenes such as ethene. In ethene, one sp2 orbital of each carbon atom overlap to form a sigma bond. The overlapping of the sp2 orbital forms a sigma bond with itself and with hydrogen, while the unhybridized 2p orbitals overlap above and below the plane to form a pi bond. Like now, this is cyclical ethene molecule, double bond, and we have two hydrogen bonded to it. Now a question can come: how many bonds is this carbon having? How many bonds is this carbon forming? So now we see that carbon is forming 3 bonds. Why? Because it's forming bonds with 3 atoms surrounding it, which is the 2 hydrogen atom and this carbon atom. Or we can say from the sp2, or assuming you don't know which hybridization, they can ask you which hybridization is this carbon in ethene molecule forming. Is it sp3? Is it sp? Is it sp2? What will be your answer? Now from this sp2, we see that we have 1, 2, 3, that is 1s and 2p orbitals. So from here we can see that carbon is forming is bond with 3 elements, with 3 atoms surrounding it. Now since we know that carbon is forming 3 elements, let us draw the hybridization, indicating the hybridization. Now we see the carbon molecule. It has an sp2 orbital here, sp2 orbital here, sp2 orbital here. This is for the ethene molecule. So this is another carbon having the same sp2 orbital surrounding it, another sp2 orbital, another sp2 orbital. Now we were told that we have an unhybridized 2p orbital that was not participating in the hybridization, and so that one will occupy this like this, because p orbital has a dumbbell shape, so the shape will be like this. And we're told that 18 form its molecule with hydrogen atom, and the hydrogen atom has s orbital, one s, which is indicating this spherical shape, around it. So we can just write hydrogen, 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 hydrogen. Now we said they overlap, these two p orbital overlap above and below to form a pi bond. They overlap above and below to form a single pi bond. Why? This carbon, it overlap the sp2, this bond is an sp2, an s to sp2 bond, an s to sp2 bond. This carbon and hydrogen, the hydrogen is representing the s bond, and this carbon is having this sp2 bond. So this overlapping of these two bonds will give us a sigma bond. The overlapping of the carbon sp2 orbital with the hydrogen s orbital will give us a sigma bond. And the overlapping of this sp2 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 between the carbon molecules will give us also a single sigma bond. So therefore we see that carbon would now have something like this. Because of these sigma bonds with hydrogen, a single sigma bond with that overlap sp2 to sp2 with this carbon, then that p orbital that we drew like this in the two carbon, when they overlap, they form a single pi bond, and this is the pi bond, and also this sigma bond on this side with hydrogen. Therefore carbon has 1, 2, 3, 4, 5 sigma bonds and 1 pi bond, having a total of 6 bonds in an 18 molecule. Now we want to look at the sp hybridization. The sp hybridization begins with the promotion of one electron from the 2s orbital to the empty 2p orbital, resulting in two hybrid orbitals of equal energy. This thing is still telling us about the excited state of carbon, so that we can have the feeling of these three orbitals in the p orbital, these three degenerate orbitals in the 2p, and one electron in the 2s. Now for this sp hybridization, we'll be looking at alkynes. Alkynes have this kind of bond. And now for the the angle that is formed between the orbital, the sp orbital is a linear shape which has an angle of 180 degree. It is oriented at an angle of 180 to each other. They are straight line. They are in a straight line to each other. So let us draw the diagram. Now for the typical 18 molecule, ethine molecule, we can see that their molecule is drawn like this: hydrogen forming a sigma bond with carbon. Then we have a triple bond with another carbon, then an hydrogen. Now to draw this diagram, we'll simply draw our two carbon here. Now we know that In the sp, we have the 2s with only one electron and the 2p with three orbitals with one electron each. Sp is telling us that we pick one electron and one electron to form the hybrid orbital, leaving two unhybridized orbitals. So take note of these key points. We have two unhybridized orbitals in the sp hybridization. We have two unhybridized orbitals in alkynes, that is the sp hybridization. And so when we are drawing the molecular structure of the ethane, we see that hydrogen form a sigma bond with carbon. But first, let us draw the normal bonds formed by carbon. So you see this shape and see this shape around carbon first of all. Then also hydrogen forming a spherical, you see H, then H. Now how can these other two pi bonds above, how can they be formed? They are formed from these two unhybridized orbitals. So one is forming the py, this is the py, and this is the pz. The pz is forming like this perpendicular. We have the py and the pz. So they overlap, py to py, py to py, pz to pz, pz to pz. So overlapping above and below in the pz to form a single pi bond. That's how we got this first pi bond. The overlapping of these two pz orbital to form a single pi bond above. So because of these two unhybridized orbitals, we are going to have the overlap will give us the pi bonds. So therefore the ethene molecule also has 1, 2, 3, 4, 5. It has 5 bonds altogether, with 2 bonds being sigma. So the sigma bonds, total number of sigma bonds in the ethane molecule is just 2. Okay, 3, sorry, plus this one under 3, and the total number of pi bonds is 2. I've given a total of 5 bonds in the ethane molecule. Now this is just the molecular structure of what we're explaining. They have an angle rotation of 120. That's a linear of 180, sorry. That's a linear shape. Then the 2p and the 2y orbitals, they overlap with themselves to form pi bonds respectively. Then the 2p orbitals, 2p to 2p orbitals of the carbon overlap with themselves to form a sigma bond. 2p to 2y, s to sp in this carbon and hydrogen form a sigma bond, and therefore we have 5 bonds formed in the ethane molecule. Now moving to the electronic theory of valency and molecular orbital theory. Now, the electronic theory of valency suggests that chemical bonding involves the electrons in the outer shell of atom, aiming to achieve stable configuration such as octet configuration seen in noble gases. So the major aim, most what is the major aim of chemical bonding is to achieve the noble gas structure. What atom aim to what atoms aim to achieve is that stable state that the noble gases have. So they bond so that they can be stable. Now in this diagram we can see two hydrogen atom bonding to form a stable state of just two electrons. So they bond together to form two electrons, and these two electrons is stable just like the helium. They form just to form the helium atom, typical helium atom. So the hydrogen molecule is equivalent to the helium atom in stability. So this rule is called the duplet rule. The duplet rule, filling of two orbitals. That is for the first share. Then so we see that the octet rule applies to elements in the second period, lithium to fluorine, including carbon, which exhibits a valency of 4. Carbon has a valency of 4. That's why it's able to form bonds with most elements to achieve the octet configuration. Elements beyond the second period with d orbitals available for bond formation may exhibit expanded octets. They may exhibit expanded octets because they have covalencies beyond 4. Like for carbon, the highest covalency should be 4. Highest covalency is 4 for the second period. We look at molecular orbital theory. The molecular orbital theory posits that when atoms approach each other, their atomic orbitals are replaced by molecular orbitals, with one having lower energy, that is the bonding molecular orbital, then another having higher energy, that is the antibonding molecular orbitals. Electrons occupy the bonding molecular orbital to stabilize the molecule as it has lower energy than the constituent atoms, while occupying the antibody molecular orbital leads to instability due to their higher energy. So let us demonstrate this. Let us draw the diagram. Although this is the diagram explaining the molecular orbital. Now we can see that for this molecular diagram for hydrogen molecule, two hydrogen atoms they come together to form a single hydrogen molecule, but these two atomic orbitals they combine to form equivalent two molecular orbitals. These two atomic orbitals they combine to form two molecular orbitals, which are the antibonding molecular orbital and the bonding molecular orbital. So in the explanation, we see that the electrons they prefer to occupy the lower energy, the lower orbital, which is alternatively called the bonding molecular orbital. It has lower energy than the atoms themselves and the antibody molecular orbital. Hence this diagram facing up. The energy, this is the bonding molecular orbital. So the energy increases the atoms themselves have an higher energy than this bonding molecular orbital, and the anti-bonding molecular orbital has the highest energy. So electrons, when they combine, atomic orbitals when they combine, electrons likely fall down to the orbital with lesser energy, because it's easy for electrons to move down to lower energy level than to move higher up to higher energy levels. So they easily fall down to the bonding molecular orbital and occupy it. So this orbital is more stable, it has higher stability than the antibody. As hence you see separation this separation in the antibonding molecular orbital, showing that there is something like a destructive overlap. So before we end this teaching, let us look at the percentage character of S and P orbitals in each of the hybridization. Now for the sp3 hybridization, if you are asked, look for the percentage S character in the sp3 hybridization. Now what are you going to do? The percentage S character, how many S are you seeing here? We have only one S and three P, with a total of 4 orbitals combining to form this single sp3 orbital. So to look for the percentage S character, we'll take this one, we have only one S present, and the total number of orbitals in this sp3 is 4 times 100. Divide 4 by 100, we get 25. Therefore we have 25% S character. Now to look for the percentage P character, we also apply the same process. We have 3 P orbitals in sp3 hybridized orbital. So we put 3 up over the total number of orbitals present in this hybridized orbital is 4 times 100. We want to look for the percentage. So 4 divided by 100 is 25. 25 times 3 is equals 75%. Therefore, we have the percentage S character in sp3 molecule is 25%, and the percentage P character is equal to 75%. So the same applies to the sp2 and sp orbitals. Now for the sp2, we have one s orbital missing with 2 p orbital. Now to find the percentage S character in the sp2 hybridized orbital, we have only one present, and the total number of orbital in the sp2 is what? 3, all over 3 times 100. Now 3 divided by 100, 100 divided by 3, we are going to have approximately 66 points. Sorry, 100 divided by 3, 3, we are going to have approximately 33.3% of S character. Then for percentage of P character, how many P or orbital do we have in the sp2 hybridized? We have 2 P characters. So we have 2 all over 3 times 100. 3 divided by 100 will give us 33.3. Then 2 times 3, 32 times 33.3 will give us 66.6%. So we have for the sp2 orbital, hybridized orbital, the percentage s character is equal to 33.3%, and the percentage p character is equal to 66.6%. Moving on to the last hybridized orbital, the sp orbital. The sp orbital, we have only one s and one p orbital, so they are quite equal numbers. So to look for the percentage s character is the same procedure. We have 1 over the total number of orbitals in the sp hybridized orbital is 2 times 100 to look for the percentage. 2 divided by 100 is 50. Therefore, the percentage s character in the sp hybridized orbital is 50%. And the same thing applies to the percentage p character, 1 over 2 times 100 to give us 50%. Therefore, for the sp hybridized orbital, the percentage s character is equal to 50%, and the percentage y character is equal to 50%. So they are both equal sp. So that is that. So this is the explanation for this topic. Thank you for sticking to the end. We hope to see you in our next video. Do well to subscribe and comment in the comment section where you have a question to ask. Thank you very much.